7.3 is trig substitution, a very different way of thinking about trig getting involved in your integrals. So we're going to begin with something that looks a little strange, but this is what we're going to do throughout this learning this technique. So this will set us up very well before we get to an actual integral. We're going to convert the square root of x squared plus 9 to trig. So the idea behind the integrals coming up, there's not going to be any trig in the question. There are going to be things like square root x squared plus 9. You'll see square roots a lot. You'll see perfect squares like 9 and x squared a lot, this sort of thing. So we're going to convert those into trig, and then we will substitute trig to replace those square roots and those x squareds and that sort of stuff. Okay, so practicing this will be good because this is not an easy thing to pick up on its own, or it takes a moment anyway. So what I've done is drawn a right triangle and labeled the angle theta there in the lower left. So to convert this to trig, the first thing I'm going to do is think of one of the sides of that triangle as being the length square root x squared plus 9. And then I'm going to take advantage of the Pythagorean theorem to fill in the lengths of the other two sides. So thinking about it, there's actually only one choice for where square root x squared plus 9 can be on that triangle, and that is the hypotenuse. So I'm going to put that right here. Now, why is it that I can only label this as that length square root x squared plus 9? Because if I want to fill in the other two sides with the Pythagorean theorem, I need to put the sum on the hypotenuse. Okay, now let's think through what would the other lengths be, and maybe it'll kind of all come together. So if we're saying x squared plus 9, well, then one of these lengths needs to be x and the other 3. So that this squared plus this squared will equal this squared. And the way I like to do it, if I've got a variable and a constant, I like to put the variable here and the constant here. Now, obviously, those could be reversed, but I find the setup plays out well when I do it this way. Okay, so let's look at it again. Pythagorean theorem, right? This squared plus this squared equals this squared. Well, that'd be x squared plus 9 equals x squared plus 9. This squared plus this squared is this squared. And now we can see maybe, hopefully it's really clear to people why, because these were being added, it had to be on the hypotenuse. We are going to see situations with subtraction, and then those will have to be on a leg. Okay, so far so good. Now we're just getting set up here. We need to convert this to trig. Well, how's that going to work? Okay, looking at my triangle, here's what I'm going to do. I'm going to pair that length that I want to rewrite or convert with the constant. Okay, don't pair it with the other variable. Which trig function is going to connect the 3 and the square root x squared plus 9? Well, that had to be cosine, right? The cosine of theta equals 3 over square root x squared plus 9. And we're well on our way. What I'll do is multiply the square root over here, divide the cosine over there, but when I divide by cosine, I'll just think of this as 3 secant theta. And there we go. We have converted square root x squared plus 9 into a trig function, 3 secant theta, based on that triangle. Now you might think, well, what would happen if we were to have reversed the x and the 3? No problem. Then you would just take sine, because the 3 would be here. It would be sine theta equals 3 over this, and so you'd get 3 cosecant theta. And maybe that kind of tips you off in why I prefer to use the x here and the 3 here, because when it comes to an integral, I would rather work with secant theta than with cosecant theta. That just seems more natural. I think most people agree with that. Okay, this is great. Let's see what we've got in our first integral here. So these are the sorts of things, these are what problems are going to generally look like. Powers of x, square roots, perfect squares. So let's take a look at integral x to the third over the square root of x squared plus 9 dx. And we're bringing back that x squared plus 9. Hey, why not? Let's connect it all. We did that work there a moment ago. Okay, so the first thing we would do here, and since we already wrote it out, I won't do it again. The first thing that we would do is be like, okay, I need a substitution for my x square root x squared plus 9. Okay, and so I would draw this triangle, and I would start to label the sides just like we did. And I'd realize, okay, its cosine theta is 3 over the square root. So that, when I move things around, is 3 secant theta. And I just wrote that underneath here again. Okay. So my denominator, in a moment, I will be able to replace with this. But there are other pieces to this integral, right? Actually, two other pieces. There's an x and a dx. We need to find substitutions for all of these. For the square root, for the x, for the dx. Okay, so let's take a look at the x. Well, I got to go back to my triangle. So looking at my triangle, how can I get a substitution for x? Well, I see the x here. And I'd like to combine that x with the constant. I don't want to combine it with that. So as I look at my triangle, hey, this is tangent. The tangent of theta is x over 3. This is great. Then I'll multiply the 3 over, and I'll say 3 tangent theta equals x. Okay, so in a moment, I'll be able to replace the x with 3 tangent theta. Now there's one more part that we cannot forget about, and that's the dx. Just like in a u substitution, we replace the dx with the equivalent du. Same thing here. We need to replace this with a d theta, and the equivalent d theta, I should say. How are we going to be able to do that? So it turns out finding x here really serves two purposes. So one purpose, and kind of the way we think about it is, oh, well, I want to be able to substitute for x cubed, so I need to know what x equals in the from the triangle. But at the same time, it sets us up to figure out what dx should be. Well, if 3 tangent theta equals x, take differentials of both sides. 3 secant squared theta d theta equals dx. So a dual purpose in getting the x for this problem. Okay, now we're ready to go. We got all three pieces. Let me slide this way up. There we go. So we've got 3 tangent theta is being cubed. Our denominator was just that root, so that's 3 secant theta. And our dx, we're going to multiply by 3 secant squared theta d theta. And we've done the substitution. We turned our x's into trig. Pretty cool, pretty nifty. And now the hope, of course, is that after we simplify, we're going to be able to do this trig integral. And it's not uncommon for these to simplify very nicely. Here, we can see the 3's cancel and one of the secants even cancels. And then we will do the cube here. So I've got that on the next page. Maybe we can keep this one on the screen. Something like that. All right, so our 3's canceled, one of our secants canceled, so the 3 cubed gives us the 27, tangent to the third, and one of the secants survived d theta. Okay. Now at this point, I realize I need that trig integral guide again. So I'm going to pull that up. Maybe you do the same. Let's see, I have an odd power of tangent and an odd power of secant. Okay. Well, I think that's option number 2 there for the secant tangent style, an odd power of tangent and at least 1 power of secant. Okay, so we're going to separate a secant tangent, setting us up for, I think we can get rid of this now, setting us up for a u sub. So if we're making our du is set up to be secant tangent, so that means our u needs to be secant. Okay, we're going to need a trig identity there. Rewrite that as secant squared theta minus 1, and then go for our u sub. Okay, so that's a very nice u sub. 27 integral u squared minus 1 du. Which gives us 27 1/3 u to the third minus u plus c. And cleaning that up. Oh, cleaning up and putting our u back in on the same step. No problem there. So we've got the 9, and then from a few steps ago, u was secant theta. So we've got secant to the third theta minus 27 secant theta plus c. Looks good. Now you might think this is the final answer, but it is most definitely not, because the original question had x's, and a few steps in, we converted those to trig functions with theta, and then when we were working with those, we used a u sub, right? So we've turned the u back into theta, but now we need to go all the way back to x. How's that going to work? Well, maybe I'll grab the previous page here. Secant to the, we have secant theta in both cases. And if you recall from before, we had square root x squared plus 9 equals 3 secant theta. So we can divide that 3 over and then replace our secant thetas. And I think I just went ahead and rewrote that. Yeah, just kind of reminding us there. This is what we had done earlier. So this is kind of like, remember this? Okay, so that can go into both. And I just went ahead and did the whole thing from this point. So let's see, when we cube, we'll have the 27 in the denominator, so that would make 1/3 out front. And the cube of a square root, we could think of that as a 3/2 power. Okay. And then when it goes in here, a little bit easier, 27 over 3, and then the square root plus c. There it is. Okay. I think that's pretty good for a first video on this section. See you in the next one.